Okay, good morning, everyone. I'm Saidur Rahman. So this is my first time at Camlis, and I'm very much excited, especially because most of the people who have, over the years, advised and mentored me are actually here, including my advisor, Matt Wright, my mentors from Mandiant, Google, Philip Tully, Ethan Rudd, and Devil Krislov. And of course, we are missing Scott. So Cambly seems to be a very nice fit for our paper, MADAR, Efficient Continual Learning for Malware Analysis with Distribution Error Replay. So we had to change from diversity error replay to distribution error replay for some reason. So this is joint work with Scott Coull, Shi and Matt Wright. And in this talk, we'll discuss our novel efficient continual learning framework for malware classification. So before going deeper into continual learning, we will first discuss some of the statistics to understand the significance of the problem. One of the prominent reasons of the rapid growth of cybercrime is the growth of malware to exploit different types of endpoint systems. And among other regions, nowadays it is relatively easier to develop malicious code, and you can put that to the internet, which will do your job to spread to different types of systems. And looking into the latest statistics from AV-Test Institute, we can see that the number of malwares and potentially unwanted applications have grown from 200 million in 2013 to 1.2 billion in 2023, which is a growth of 600%. So to protect different connected computer and network systems, antivirus vendors are also pacing towards developing new tools, techniques, and inventing new technologies to detect and classify this malware. One of these techniques is supervised machine learning techniques to detect and classify malware. Among other detection techniques, static malware analysis is widely adopted in industry in which expert-designed features are used to design the system. And these systems have achieved remarkable performance, such as Light GPM model on a benchmark malware dataset Ember has achieved a ROC-AUC score of 0.996. So looking into the malware growth statistics in a little bit micro level, we can see that AV-Test Institute detects around 500,000 new malware and potentially unwanted applications each day. In addition, VirusTotal, which is another popular crowdsourced engine, registers 1.8 million unique pieces of software each day. This huge volume of new malware and software releases cause antivirus vendors incremental cost and training times. To handle these challenges, antivirus vendors have three less than ideal options. Firstly, they can expand tremendous training effort to frequently retrain the model over all the accumulated data, which does not necessarily solve the problem. Secondly, they can remove some older samples while retraining with new data, which provides attacker an edge to reuse older malware variants instead of writing new malwares. In addition, the model actually will forget those removed samples eventually. Finally, they can train less frequently at the cost of not adjusting to changes in the distribution which enable a novel malware to evade systems relatively easily. This is a picture that I took while I was living in Rochester. It's the same tree outside of my apartment in different season. So actually, I thought it's a perfect way to show the distributional shift in a much more easier way. So it's hard to show distributional shift in malware, visually. So now that we know the significance of the problem, we're going to motivate our solution. Continual learning is a branch of machine learning which acknowledges the continuous distributional shift in the data. Essentially, a continual learning-based model learns non-stationarity or non-stationary data which are observed periodically or in a different time period. The data distribution of each of this time period is different. In continual learning literature, data from each time period is often referred to as task, or this task can be for malware domain, new malware families. It can be new samples of existing malware families, or even it can be new objectives of the model. We can see a schematic representation of this from, oh, okay, I haven't changed the slide, sorry. Okay, so we can see a schematic represent, okay. Because I'm managing two, so I think there's a synchronous problem. Anyway, so we can see a schematic representation of continual learning and inference. Let's see in this figure, and at the start of the continual learning training, the model learns data from data distribution one. And in the next iteration of learning, the model learns data from the time period 2, and the inference objective is to identify whether a test sample belongs to data distribution 1 and the data distribution 2, and the process continues. So continual learning is fundamentally inspired by human learning process. We learn by observing new things, new objects, and the learned knowledge is somehow stored in the hippocampus of our brain in the form of an abstract representations. The two major benefits of continual learning is the relaxation of the need to store all the data, which eventually reduces storage cost for our problem space. It can reduce computational cost as well by relaxing the requirement to retrain over all the available data. However, unlike human brain, a continual learning model is prone to catastrophic forgetting, which causes a model to forget the learned data. In a security application like malware classification and detection, forgetting has a serious consequences because it would essentially reintroduce the vulnerabilities in the system. So before going further, let's briefly talk about catastrophic forgetting and why that happens in the model. Looking into the early literature of machine learning, we find that catastrophic forgetting is a very, very old problem of neural network, and in which model forgets the old task or old data distribution. Looking into this figure, let's assume that the first task of continual learner is to learn and to classify between cat and dog. Then the model learns the second task, which is to classify between tiger and elephant. Because of the catastrophic forgetting phenomena, the learner will have difficulty to classify cat and dog after learning task 2, which is tiger and elephant. So at this point, we'd like to formalize how continual learning actually is kind of applicable to traditional malware classification pipeline. So a typical malware classification pipeline follows first identifying whether a test sample, test software, is a malware or goodware, which is a binary classification problem. Then in the lower level, we try to understand or identify the family of the identified malware, which is a multi-class classification problem. A family is a set of malware programs that have significant overlap in their code, such as they are considered by experts to be a group with common functionalities. The last layer of the pipeline is to identify the broader category of the malware or behavior of the malware, such as adware, ransomware, which is also a multi-class classification problem. Now, combining continual learning scenarios within the malware classification pipeline, we propose a formalized continual learning scenarios specifically for malware domain, where domain incremental learning considers the distributional shift with the emergence of new malware and benign software. Class incremental learning considers the emergence of new malware family, and task incremental learning considers the emergence of new malware category. Furthermore, we propose a novel threat model in which an adversary can exploit the catastrophic forgetting phenomena. The attacker can reintroduce and reuse some older malware variants to evade the detection systems, and we define this attack as a retrograde malware attack. So our prior work actually shows that current continual learning techniques are insufficient to overcome catastrophic forgetting phenomena in malware domain in all of the continual learning scenarios. We show results for domain and class incremental learning. For domain incremental learning, none of the For domain incremental learning, none of the continual learning techniques are effective, and all of them perform very poorly. And for class incremental learning, a majority of the continual learning techniques failed, except Coull, which shows marginally better performance compared to joint baseline performance. So now for this work, we first tried to investigate why the SOTA continual learning techniques failed in malware analysis domain or malware domain. Note that we have performed several different exploratory analyses, and for the interest of time, we'll just show a few. So in this table, we are saying the frequency of malware and goodware samples in each task month for EMBER dataset. And I would like to get your attention to the last column, which is, you can see number of malware families, and the second last column, which is number of malware. The number in this third column indicate that this many number of malware samples actually are coming from that many number of malware families. Let's look into the January data a little bit more closely. This is really interesting to see that around 32,000 malware samples is coming from more than 900 families. And if we consider each of the month's malware data distributions as a bigger cluster, each of the families actually under the hood, they form smaller clusters. And this is also indicative that malware data distributions are heterogeneous in nature. So in another level of analysis, we can see that how many new families are observed in each of the task month. And we can see that in January, the model learns 913 families, but it does not observe a sample from all the families while learning in February. And rather, it only observes 551 families and 425 new families, as you can see in this plot. And the emergence of new families are observed in each of the task month. Again, this is analysis based on the EMBER 2018 dataset. So summarizing the exploratory analysis, we can say that, again, we have tons of other analysis. We refer to the paper if you are interested. So malware distribution in each task contains samples from on an average around 800 families. In each learning episode, we observe samples from a lot of novel families, and older families are observed infrequently, making the problem more complicated. There are a substantial number of samples in the distribution that do not have AV class labels. Finally, the priorities of the malware families changes over time, meaning that prominent families which look like they have tons of samples at the beginning of the learning episode, they do not actually remain prominent at the later part of the learning episode. So taking into account of all these properties and challenges of malware data distributions, we propose our novel continual learning framework, MADAR, malware analysis with distribution error replay, a novel replay-based continual learning technique that can maintain heterogeneity among the replay samples. Prior work emphasized the need to replay both representative and discriminative samples for an effective replay-based continual learning technique. MADAR is designed in such a way that captures the heterogeneity among the replay samples. To that end, MADAR selects based on family distribution to accommodate varying families, and it also considers selecting samples which are closer to each other and also farther away from each other. You can label that as outlier, but we don't do that necessarily here. Essentially, the MADAR picks samples which are farther away from the cluster mean. MADAR consists of two variants, which we will look at later slides. For each of the variants, we perform experiments with another two subvariants, and for the interest of time, we'll omit the details of those two subvariants. As we have mentioned, MADAR is a replay-based continual learning technique. So hence, let's briefly discuss how actual replay works in continual learning. In this schematic representation, one indicates the initial phase of the training, where we initialize the model by training with the available data that we have today. Then we store the training data in a repository. After the initial phase, the model becomes a continual learner in phase 2, where it observes new data and some of the stored data using a constraint replay buffer. The key question of any continual learning technique is to investigate different ways to fill out this replay buffer with a given budget constraint. MADAR finds efficient and effective way to select samples from the storage with a given memory budget to optimize the performance of each learning episode. Here we present a simplified schematic representation of the first variant of MADAR, which is based on isolation forest-based sampling. In a high level, we attempt to explain the process of MADAR sample selection in light of the replay-based framework that you have just seen in the previous slide. Assuming that after task 1, we have data stored in each family in a storage, and the model is transformed to a continual learner model in phase 2. When task 2 data comes in, we get the replay samples using isolation forest module with a memory budget from the stored data to fill out this replay buffer. You can see that the process of sample selection from the storage is based on each family, as you can see in this figure. Meaning that the MADAR select sample is strictly maintaining the family-based representation. After selecting the replay samples in the replay buffer, MADAR combines the new data that just came in and also the replay data to get the training data for task 2 to retrain the model. In this way, actually, it reduces the requirement to use all the previous data. The second variant of MADAR is called the MADAR theta, which is based on learned weights or learned representation from the previous learning episode. We explain the process in this schematic representation. MADAR theta still uses isolation forest to select samples from the storage. However, instead of processing the raw samples or raw features, MADAR theta is designed to first extract the learned hidden representation of a specific layer. We tried out different layers, but there's we finalized the last layer before the classification layer of a specific layer from the trained model of the immediate previous learning episode, and then use isolation forest to identify the anomalous and similar weights. Afterwards, MADAR theta uses a backtrack mapping function to identify the sample corresponding to those anomalous and similar weights to select the final replay samples based on the memory buffer constraint and fill up the replay buffer. Finally, after getting the replay samples in the replay buffer, MADAR theta combines new data and the replay data to get the training data for task 2 to retrain the model. Note that MADAR theta is significantly faster compared to MADAR, as the hidden representation can be in much more lower dimension than the original feature space. So in addition to Ember benchmark, we have collected 2 bigger Android malware dataset from Android's repository for domain, class, and task incremental learning, and I'm omitting the details for the interest of time. So we evaluated MADAR and MADAR theta using both Windows and Android malware datasets. As we have mentioned briefly that there are 2 subvariants for each of the proposed techniques called ratio and uniform, indicated by R and U in this result table. We compare our techniques with state-of-the-art techniques and 3 baselines. MADAR and MADAR theta actually outperforms prior work significantly. To put you into the context, joint baseline, as you can see on the top, actually this is with Ember. Joint baseline with Ember, you can see that it achieves 96.4% accuracy, and the number of training samples are 670,000. Whereas MADAR yields similar level of performance with only 200K training samples. And we observed the similar performance boost or some performance gain with Andrew's dataset as well. In class incremental learning, our proposed techniques also outperform prior work with significant margin. Comparing with joint baseline with Ember, which yields 86.5% with 303,000 training samples, our techniques require only 20,000 training samples to attain similar level of performance, and we observe similar performance gain for Andrew's dataset as well. For the task incremental learning, finally, our techniques show the similar trend of performance gain, and compared to prior state-of-the-art and baseline, our techniques are significantly better. So to summarize, in this research, we attempt to bridge continual learning and malware domain for an ever-evolving malware classification system. Our results from first papers show that computer vision-based techniques come short to address catastrophic forgetting phenomena for malware classification. In addition, our analysis show that malware data distributions show a significant heterogeneity among and within families. Towards that end, we proposed a novel distribution error replay technique for malware classification, which yield state-of-the-art results in several configurations. Specifically, our technique shows significant improvements in class incremental learning scenarios for both Windows and Android malware datasets. In addition, ratio variants work better for domain incremental learning scenarios, and uniform variants work better for class incremental learning and task incremental learning scenarios. The takeaways from this talk, we'd like to conclude with some takeaways. Firstly, the rapid and evolving growth of malware is a challenging problem for industry. Ideally, we would like to design a defensive system that can be ever evolving, as well as it can be intelligent enough for effective malware classification and detection. Secondly, continual learning is an ideal candidate that can help to address those challenges in the malware domain. However, we must consider the unique nature and complexities of the malware data distribution to design the intelligent system. Finally, our proposed continual learning framework, MADAR, tailored for malware classification, achieves state-of-the-art performance in several configurations. With that, okay. Thank you. If I'm ready to take some questions.
Hi, can you talk more about the feature extraction techniques that use in MADAR data?
Do you mean this technique? So basically, first, in the prior episode, for example, if you give an example for Ember, we splitted the data month by month from January 2018 to December 2018. So first, if you train your model with January data, then you get a kind of a model, a prepared model, which gives, I don't know, 95%, 96% performance. So once with forward pass, you can actually get the hidden representation before the classification layer. So once you get those hidden representation, you can flatten those and then send that to isolation forest to split the feature representation into some sort of dimensions where you can see which weights or hidden representations are close to each other and which representations are a little bit farther away from each other. Based on that, you kind of then send to this mapping function that, okay, these hidden weights which are anomalous, what is this particular samples referred to? What is the original feature space for that particular anomalous hidden representation?
Thank you.
So as a co-author on the paper, I prefer the pronunciation MADAR like radar.
Thank you.
I'd be curious to know what sort of real-world data you have on these RMA-style attacks actually happening. Or maybe I missed this part.
Could you please probably talk a little bit more about that? What do you mean?
So there's this RMA-style like retrograde attack where I guess models have forgotten the old families of malware. Do you have data on these occurring? Like the rates that this happens at all?
Oh, so we do actually, but not for as part of this paper. So the question is basically this. Let me go back to retrograde malware attack. So recently we have submitted a paper to another venue, so it's on the verge of it's in the review. So I'm going to share a few of the findings. So assume that you have an antivirus installed in your system, right? So it's pretty easy for you if you know, well, this antivirus system is actually trained with this type of data. Let's say Ember data, right? So you know this Ember data is available, publicly available, and now You can do as an attacker actually some as a gray box access because you have access to antivirus. So if you do run through this kind of model and you do some sort of kind of finding out, that they are training with continual learning in continual learning mechanism, you can find out the probabilities of particular unknown samples, right? Now you can create a mapping. If you introduce a new malware variants, for example, adware, the effectiveness of this antivirus system is actually get reduced for another variants, let's say ransomware. If you can map that, we did kind of try to map that. If you can map that, you can utilize that knowledge to create variants of malware that we show in the legacy samples. And that variants of malware actually will be effective to evade the detection system. Did I answer your question?